There we go. It is now being recorded. Um, all right. So first thing first, we're going to talk about the function called program submission. Um, so that's going to be the first thing we'll be working on, and then we'll talk about potentially structures at some point in today's class. And you have a new homework assignment too. So the today's setup is going to be the same as on last Thursday, which is you have a lab, and then you also have a homework, component that you have a whole week to work on. So that's the recursive, homework assignment for this week until next Thursday. Our exam is on next Tuesday, so don't forget, okay? Um, Especially people who are just listening to the lecture right now online and not being in class. Um, all right, so we'll go ahead and take a look at the function called program submission, and then work on that program, and then we'll go from there. All right. Uh, that is interesting. No internet. All right. And I really do not have internet. Oh, that's because I changed my password. All right. Let me give me a second here because I have to change my profile setting here. Okay. So every year I have to do this once. So let me change that. It is the password, it's the Wi-Fi security that is the issue here. Give me a second. There we go. Click save and close that window. All right, so we should be good now. Yep. All right. All right, so back to the homework assignment. So we will start with taking a look at the homework assignment, and then we'll go from there. So this one, is based on the previous lab. So that's what we're going to do is to take a look at the lab itself because all the instructions are in the lab itself already. All right, so we go back here and then we go to the function call lab. And by the way, it is always a good idea to review the labs as well as the lectures because a lot of the instructions are actually embedded into the lab instructions. So it is, I would say for studying purposes, it's always good to do that too. All right, so here is the lab. And if we are to, okay, I will just go to preview because the swap function is mentioned in, I cannot remember which question. So we'll go ahead and scan here. All right, so I think it's one of the two spacers. All right, so let's see. Not this one, maybe the last one. All right. Hmm. Where did I put the code? All right, I'm gonna cheat a little bit here. Go back to edit because it's hard to scan, but if I do it this way, I can see all the questions. All right. Well, we'll go ahead and start with this. We'll just go ahead and start with the C version of the same program. Do we have any questions about the C program? No questions about the C program? Okay. Are you sure? Because I can definitely demonstrate it in GDB just so that we know exactly what is going on when the C program works. So should we do that? Okay, I think so. I think we should probably do that first. So let me just go ahead and put this in one of the command prompts, which I cannot remember which one is up on this screen. I know I put one here. There you go. Okay. So swap.c, paste, and I forgot one thing, okay, in the C program, but most of you already know how to fix that one, which is, you need a pound include standard integer .h because otherwise, u in 8 underscore t is not defined. So what if I forget this? Okay, so let's just for a moment we just say that okay, I forgot about this entirely, and then when you compile the program, it complains about it. Okay, it says oh, so on and so forth. So the error message itself tells you how to fix it. Okay, the error message itself says uin8 underscore t is defined in header standard integer.h. This is probably fixable by adding. I mean, come on. I mean, this is super obvious. Okay, so just by reading the error message, people, I mean, students in this class should be able to fix the program. So anyway, I'm just going to go back and fix the program like so. Oh, int.h. There we go. All right. So what we'll do is we're just going to compile the program again. Okay, now that I fixed it, and then do a GDB of this exact program, and I list the program here. So the first thing is, I will have to put a breakpoint on line 16 at least, okay, because that's when the program stops. I'm going to put a breakpoint on line 15 as well. Okay, so right before the call to swap, I will pause the execution of the program just so that I can examine what is in X, what is in Y, and then I'll single step into swap to find out what's going on in swap. Okay, so run the program. So at this point, I'm right before swap, or the call to swap, I want to print out what is X. And I was also want to print out what is Y. Okay, predictable. Okay, X has a value of 3, Y has a value of 7. That's totally predictable. So now a single step into the swap function. So now I'm in the swap function. The first thing I need to make sure that I need to look at would be what is pointer 1 and what is pointer 2. So pointer 1 is dd3f something, and then pointer 2 is dd3e something. One has a 3 in it. The other one does not even look like it has a 7 in it, but that's basically what 7 looks like when it is interpreted as an ASCII code. Okay. So one thing you can also do at this point is to change the frame. This is one of the really, really useful feature that you will find useful also in CISP 400, 430, and most of the other classes where you have to write programs in C++. So let me show you what this can do. So you can basically just type frame or BT. Okay, if you type BT, it will show you that there are two frames. Frame 0, which is where we are now at, is the swap function. Frame 1 is in main. So instead of asking, oh, where is X in main, you cannot ask that question now. Okay, if I say what is X, it is not in the current context because the current context is in frame 0, which is inside the swap function. Okay, but you can switch the frame. You can say frame 1. So that would switch the frame back to main, which means now you can interrogate the debugger and ask about variables in main. So now we can print X. Okay, now we can print Y, but that's not what we're interested in. We want to know the addresses of X and Y. So you can now say, what is the address of X? What is the address of Y? And now we can see that, oh, okay. So we can see that the address of X ends with DD3F, which is PTR1, and then the address of Y ends with DD3E, which is matching PTR2. Is that okay? All right. So I think this is actually really important is to use the debugger to help you understand and also bridge what you're learning in this class to general C++ programming. Okay. And I think if anyone before this class had like any questions about what pointers are, I think this really also helps to illustrate what pointers really are when you're writing programs in a high-level programming language. So I'm going to go back to frame 0, okay, because I want to trace this code. So what T would end up with is going to be whatever PTR1 is pointing to. So T is not going to be PTR1. It is what PTR1 is pointing to, which is a value of 3. Okay, so if I single step, I can now see that, oh, okay, it really is 3. And the next statement on line 7 is taking whatever PTR2 is pointing to, and PTR2 is pointing to 7, okay, a value of 7. So that becomes the right-hand side of line 7. and it is going to be used to update whatever PTR1 is pointing to, which we also know as local variable x of main. Okay, so this part is going to be the most interesting part because when you single step this part here, then we can also change the frame again. We can go back to frame one, which is main, and then we can now ask, okay, show me the value of x at this point. It should now be a, okay, there are two choices here. It's either a 3 or a 7. It was a 3, but we used the 7 to override it. It is now a 7. Okay, so this is the most important part of using the debugger is you can switch between the frames, look at things from the perspective of different invocations of a function, and then you can now go like, oh, so swap has a pointer pointing to a local variable of main, and therefore swap can change the local variables that belong to main. Is that okay? Okay, we're doing okay so far. So your assembly code should do this, basically in the same way, in a very similar way, except you'll be using, TTP as an architecture, but the function of swap should still be the same. You're not switching, you're not exchanging the parameters, you're exchanging what the parameters are pointing to. Are we doing okay? All right. So now when we write this code, okay, we can now basically write it in either the way of using one single pointer and just move it around, or we can use the more systematic way of doing this. I'm going to use the more systematic way of doing this. So we'll go ahead and copy the C code to the TTP ASM code. Okay. And I actually, okay, that actually may not be the way I want to do it because I want to actually copy and paste the template of the code that I have given you to begin with, which is down here, right here. Okay, so this is what I really want to copy and paste first, but then I also want to copy and paste some of the C code. So I'll copy and paste this one over here first. Um, mm, okay, maybe here. Okay, I'll just stash it right here. Okay, and I can get rid of just about everything except for swap because that's what I'm trying to implement. And main is already done, so we can just kind of take that out. There we go. All right. So at this point, we are right at the entry point of swap. I really want to know what is on the stack. Okay. So that means to investigate this, all I need to do, okay, is to comment out the code after this, replace all the beginning with a comment like so. And then we put a halt right here. We don't even do a single thing in swap because I want to know what is on the stack at this point. So this is really important because now you can understand, what are the two parameters? Where are those two parameters? I mean, where are the parameters and where are the local variables x and y and what values do they have? Okay, so I think this is a really important exercise. So we'll go ahead and run this in a different window. Okay, so we'll go ahead and run this in um, documents, CISP 310, Reefer Spider, and we'll go ahead and submit this job. So what I'm illustrating here is also something that might be useful for your next homework assignment, implementing Fibonacci, because the whole idea is the assembler is built to give you the tools to help you understand the concepts. So if you use those tools, it really should be helpful. So now we are going to go to the share folder and I'll create a new spreadsheet for today. So I'm doing some of the documentation, but you really should be putting this in your own notes too, because reading somebody else's explanation and listening to somebody else's explanation is not the same as writing your own. Okay, so that's a whole different process. All right, so we'll go ahead and do the usual thing. Okay, we'll go ahead and simulate a few instructions here or a few locations. So this is going to be this location -1, and then we turn everything into hexadecimal. So decimal to hexadecimal, starting with this, and now we can Drag this down, and then we'll just go ahead and go through. That's more than enough. All right. So now we go back to the C program like this. And then we want to see how the stack is going to be used. So this one does not really use the entry code to call main. So the entry code itself is main. So that means the local variables x and y, they are allocated here and they got their values over here. So this is another way of doing it. And tracking what has which register has what at this point is really important. Okay. Um, so according to this, okay, decrement D allocate for local variable y, and then decrement D again to allocate for local variable x. So that means in terms of the map, we have this location being y of main. We have this location as x of main. And then we switch back to the assembly code. There you go. And then we try to see what is happening here. Increments, okay, copy register D to register C, increment C, so it now points to Y again. Load A with 7, and then store A to whatever register C is pointing to. So that means we're initializing local variable Y with a value of 7. So I go back to my spreadsheet, okay, and just say that, okay, we just initialized this with a value of 7, and go back to the code again. We decrement D to allocate for the second parameter. Oh, there's a 3 here. Forgot about storing the 3. So the 3 was stored right after I allocate for local variable x. So that means at that time, register D, the stack pointer, is pointing directly at local variable x. So I just store a 3 to whatever register the stack pointer is pointing to, which is local variable x. Yes. Hmm? Yeah. Um, did I haven't changed the due date. Oh, okay. Okay. The 18th. So that would be next Tuesday, which is also going to be our exam. That was, oh, okay. Maybe that is the case. Well, if that's the case, I can still go through this partially so that you guys can, at least get some ideas. Some people have turned in the answer to already. Um, what about the rest of the class? Do you remember the discussion? Well, it's on the assignment itself that it was due today, but I think I might have mentioned something about postponing that. Mm-hmm. Hmm? Okay. All right. Well, because everything is recorded, I can I can go back and check. But I trust you guys. Okay, so I'm gonna say I will still kind of go through this at least partially, so this way people who are not done with the homework at least has some kind of a starting point. Okay. No, no, no. You did not misheard me. I just have to change the due date, in the actual lab. So I think it's this one, and let's make it due a little bit later. Okay. That's all. That's not a problem. All right. So we'll change the due date to the 18th. So if you have turned in something already and you are not really sure whether what you turned in is going to work or not, now is your chance to go back and kind of fix up your program if you have time to fix it now. So click save. There we go. Okay. But I will still go ahead and explain what I have done up to this point. Um, right. So we go to the document, change it to today's date, 1113. There we go. So the 3 is going to be here. And then we are going to push. Okay, so if we go back to the code of main, so I have not touched anything in the swap function. I'm just explaining stuff that is happening in main. So the next thing I do is to store Okay, so we are done up to here. We initialize y. Then I decrement d, which means now the stack pointer is pointing to location 253, and then I store c in it. So at that point in time, c still has the address of y. So that means in terms of what the stack looks like, this is going to be the PTR2, which is the second parameter of swap. It now should have a value of the address of y, which is ff, and then I would push the next one. Okay, so we'll go back to the code here. So I decrement d, okay, to reserve another byte on the stack. Decrement c. So decrement c, after I decrement c, c now is the address of x instead of y, and then I push it on the stack, and then I push the return address. So if I go back here, this is ptr1 of swap, and that's going to be fe in this case, and then we have the return address to main from swap, and that's going to be at this location. So this is just a return address. I'll just put a question mark here because it depends on the actual location. So that's how the stack is supposed to be set up at this point. When the program is done, okay, when the program is done, we need these two values to be exchanged. So that's the objective of the swap function. Yes, we want to switch the values in RAM. So that means that when the program is done, when swap is done, we need this to be 7 and this to be 3. That should be the result of running swap. That's what it looks like to begin with. Nope, you from swap's perspective, from the swap function perspective, this is all you know. You cannot use any information other than whatever the stack pointer points to, and these 3 bytes are is the context, is the frame of swap. Other than this, you cannot use any other information. Mm, you know, well, okay, since the return address is here, it is at it's basically this is called the top of the stack, because it's the last item that's pushed. So the stack pointer is always pointing to this location unless you have to push something else on the stack, unless you have to reserve a byte, which you do because swap has a local variable. So that means you have to deallocate the local variable first before you can say, okay, stack pointer, you're now expected to be pointing to the return address, and then you can use the usual return code. Yep. Yep. So is that helping a little bit? Okay. So if you have not set up Reverse Writer, once again, it is kind of useful, okay, because it really shortens the development time of of running your code. You can test out things, put halt instructions at some place, figure out what is happening up to that point, so that you can track your code a little bit more effectively. So I would definitely suggest people to, if you have not done so, install Reverse Writer, okay, and get it to work. All right. So, well, thank you for reminding me that the due date is supposed to be next Tuesday and not today. I did not plan on lecturing today because um, the interview was supposed to be the whole day, and then they found out that they did not have a whole lot of candidates, so they can push everything into the afternoon from 1 o'clock to 4 something. So that's why I was able to teach the class again today. But it is a position called ISA, or Instructional Services Assistant. Those are the people on campus, who put in the schedule, who handle all the extra time payment and whatnot. So they are, it's very specialized because they have to know how to use the various systems to track, the schedule, after the departments or the divisions have determined, okay, this is what we want to offer next semester, and then they have to put it into the system, double check, are we double booking a classroom, and so on and so forth. So that's the person that we're hiring because the person who was in this position, got promoted to the district office. So now we have to hire again. Alrighty, cool. Okay, so today's lecture, we're going to start with structures. Have we started with structures? Just a little bit? Okay, very good. So we're going to continue with that discussion, but before we go any further, this is your current homework assignment. It's called recursive call. This is what you need to do in the lab, and this is what you need to turn in next Wednesday. Okay. Um, and in it, okay, I will click on it, and it's no big deal. In it, it will say, oh, okay, I thought I put it here already. But anyway, um, one of the previous labs may actually be useful for this one. So I would suggest you guys to take a look again at one of the previous labs. I'll point to which one. It is the one that talks about params and return value. So you, if you have done it already, you can still click on it. It is one of the code, I think it's even the first question, that is actually important. Okay, so anyway, take a look at this one. Make sure you understand everything about this particular lab before you start with the recursive function lab. Okay, because that one, not so much the lab. The lab today is not a big deal. It is about the implementation of the code. So for the next week or so, you have to kind of make sure you go back to this one first. All right, so we're going to go back to structures. All right, so let's go ahead and get up of this one, and then we'll go take a look at structures. Okay, so we'll say, struct.c, and we'll go ahead and delete it. There we go. All right, so as usual, we have to pound include standard integer.h because otherwise I cannot use uint8 underscore t or anything like that. I'll define a structure called x, and we'll just go ahead and say uint8 underscore t. We have member a. Oops, there we go. And then we have member b, and then we'll have member c. Okay, so pretty basic here. And then in main, okay, this is main. Main is going to have a local variable. I'll just call it var1 because I have no idea what we're going to use the structure for. And what it will do is it's going to call a function. We'll call the function f, and we're going to pass the var1 to function f, which is for initializing all the elements. And that's all we want to do. So here is f. It returns a void, and it has a parameter, which is a struct x star ptr. So that means ptr is a structure to a struct x. And all we want to do is to change a, and then we want to change b, and then we want to change c to, let's just initialize all of them to 0, 1, and 2. All right, so right away, I just did something to confuse you, okay? Because when you look at lines 10 and 11, they actually do the same thing, except one handles, member A, the other one handles member 2. But in terms of what they mean exactly the same thing. PTR is a pointer to a structure, and I want to change member A on line 10, and I want to change member B on line 11. But in both cases, both of these statements is changing the member of a structure that is pointed to by PTR. I'll be okay with those concepts. All right. So we'll go ahead and make sure this code works in C++, and then we'll implement this in assembly. So save it first, okay, and then gcc-g-o struct.c, okay, and we just run it, okay. Oh, that's not going to do anything. There's no output. All right, so we'll put a breakpoint on line 18. We run the code up to line 18. So you can, if you want to, print what is in var1. It's not going to be very exciting. It's not initialized. So now we single step into the function, and now we ask, what is pointer? So pointer is the address of the entire structure. So it kind of matches what we saw here. Well, actually, we can change the frame back to main and then double check that the address of var1 is indeed something ending with dd3d. So we use the same trick as before, switch back to the main frame, and then we ask, okay, what is the address of var1? Ah, okay, now we're convinced because it really is dd3d, and then when you look at the parameter ptr, it is also ending with dd3d. So now we change the frame back to, yeah, we can change it back. So we'll just go through one single initialization. Okay, we just went through line 10, and then we go back to main, okay, frame 1, and then this time we print var1 again. And you can see how member A is changed already. Okay, so you can see how var1 dot A, which used to be 127, is now a 0. Okay, so that's how this works. And then from a previous lab, we also did something like, okay, where is the beginning of R1? Where is member A? Where is member B? Oops, there you go. And where's member C? All right, do we see a pattern? Okay, yep. So the first member is at the very beginning of the entire structure. The second member is right after that, and then the third member is right after the second member. Okay, so all of this is important. Okay, so we're gonna stop the debugging or the debugger at this point and copy the program to struct.ttp-asm. And now we want to look at, okay, what about the assembly language implementation of this thing? So we'll go ahead and comment out the C code so they are still around, just, oh, okay. Okay, let me do that one more thing, one more time. Replace the beginning with / with a space. G, there we go. Okay. So now we use the more usual way, which is using the entry code. We initialize the stack pointer, decrement the stack pointer, and then specify the return address. Oops, there we go. And then stda. Actually, I need to exchange these two. So that would push the return address on the stack. JMPI to main to continue execution in main. When we are all done, go back to halt as an instruction. So that's the usual kind of typical entry code. And now we have to define struct. So the way we define the structure in assembly language is not, there's no syntactical thing that we can use to define a structure. So a structure is really defined as labels, okay? Where the label names is going to say, okay, this is the displacement from the beginning of a structure to a specific member. So that's how we're going to define the labels. So x_a is the offset in number of bytes from the beginning of the structure to member A. And that would be 0 because the first member is at the very beginning of the entire structure. We saw that in the GDB, in the debugger. The next one is B. I could have just said 1, but that's not the way I like to do things. I would use x_a 1 plus because it is 1 byte after where we can find member A because member A itself is only 1 byte long. And then we can use the same approach to get to the offset to member C. It is 1 byte off from where we can find member B. And then we add one more, which is the size of X. It is the offset to the last member plus the size of the last member. So this is how we capture the structure, but without using any syntactical structure in assembly language programming. So are we understanding the approach, or and also how what each label is representing? So we're good. Okay. All right. So we all good. All right. All right. So we're gonna go to main. Okay. So we'll do one thing at a time. This is main. And the typical way that I write my code is really to start from the beginning and then immediately end the code. So I know that I need to basically get out or return to the caller. And this is our usual code for returning. So and then right away after that, I say, okay, do we have any local variables? We do. This is my first and only local variable. And as a result, when everything is allocated, it would be at the very base or the lowest portion of the frame of main. And that's why the offset from the base of the frame to var1 is 0. Okay, because it is the only one and only local variable that we have. And then we define LVS, which is local variable size, which is the offset to the last local variable. Since we only have one, it is both the first and the last. So this is the offset to the last local variable of the entire thing. And now we have to add the size of that thing. So it is not one anymore because this is a structure. So what should I use between main underscore var1 and the plus? Yep, x dot size is the way to do it. Okay, so now we add the size of a struct x to the offset from the base of the frame to var1. Okay, so that becomes our var size. So once that is done, I can now have the code to initialize, to allocate the space, and also to immediately deallocate at the end of the function. So LDI be with main var1, oh, LVS, subtract this much from the stack pointer for allocation purposes. And then before we actually do the return, we have to make sure that we deallocate, which means we're adding that much back to the stack pointer. So if you don't do this, okay, if you don't do line 35 and line 36, your stack pointer will still be pointing at the base of var1, and then it would use that, attempt to use that as a return address. And then your code is going to go to some place that it's not supposed to go to. All right, so with that all done, we can now implement function f. So, so that's what we can do. But I'm going to go back to the picture. Okay, so we'll go back to the picture here. I will make a replicate of sheet 1, even though it is not exactly the same, but it's close enough. So we can reuse some of the structures of sheet 1. And we call this sheet 2. There we go. So all we have to do is to erase only this part here. Okay. So this time we do have a return address from main back to the entry code. So this is a little bit different from last time. And then we reserve 3 bytes on the stack. So basically the stack pointer would be pointing here after everything is allocated. So this would be equivalent to var1.a, this is var1.b, and this would be var1.c. So these 3 bytes together is where var1 is. So do we have any questions about the map of what is on the stack? And together, all 4 bytes from here all the way here, that's the frame for main. It doesn't have any parameters, but it does have the return address and also local variables. So we doing okay so far? Okay, all right. If you do have any, yes, please. Yep. Mm-hmm. Mm-hmm. Okay. So let me see if I understand what you're asking. So you are asking what if we have in the C code, we have another struct x, say var2. Is that what you're asking? Well, then you have a var2. Then you have a var2, and this is the label to the base of var2. So that's going to be based on where you can find var1 and also add the size of var1. This will be where you find var2. So that also means that instead of using var1 and then plus the size of it to find the end or the number of bytes you have to allocate, this will be var2. So that's basically how I would define the labels. So we doing okay so far with this? Okay, all right. So I'm going to switch back to the original code. Okay, yes, go ahead. Which line? Line 40? Oh, you want to scroll? All right. So I'm going to switch back to the original code, okay, because I want the C code to resemble the assembly code. So I'm going to undo a bunch of stuff, and I think that's it. Okay, just two undos. There we go. So at this point, I can still run the code in River Spider, because this gives me the ability to kind of take a look at how the stack point is getting changed, even though we didn't do a single thing to anything in RAM. But I would still like to know, what is going on. All right, so we go back to the assembler, and we can see how the stack pointer, is initialized here. This is where we, nope, this is the old program because I did not tell it to run the correct program. Okay, that's my fault because I just up arrow and forgot to change the name of the source code. All right, so we go back to here and then we go back to the analysis tab. This is the stack pointer initialized. This is the return address. And then we didn't do anything else in RAM. All we did is to decrement the stack pointer by 3 bytes so that it points to location FC. So if you go back to the spreadsheet, this is FC. So we got everything working as expected. So that's important, okay? Because if you don't allocate a space for the structure or for the local variable var1, then what are you going to pass to the function? Okay, because it needs a place to live. So that's why we have to do this calculation and double check to make sure that the space is indeed allocated on the stack. So now we can go back to the source code and write some more stuff. Okay, so we'll go ahead and write the function f. Okay, so this is for function f. It's the entry point, and as soon as I put in the entry point, I put in the return code right away because otherwise I have a tendency of forgetting to do that. So JMPB, there we go. That's just my style of doing things. Doesn't mean that you have to do the same thing, but it's just the way that I like to do it. All right, so now with this one, you can simplify if you want to. F underscore PTR can be just defined as 1 if you want to, but personally, I like to do this. I know it is not really particularly productive, but I like to do it this way, and I'll explain why. All right, so in both ways, uh, f underscore PTR ends up being just 1. Okay, but this way, I'm reminding myself that I don't have any local variables. So in case later on I do need some local variables, I now have the template ready to handle local variables. And the parameter or the offset to find the parameter is just a displacement from the number of bytes that I need for my local variables. So I don't have to recompute everything just because, oh, I think I need a local variable now. Okay, so that's just the way that I like to do things. Doesn't mean that you have to do it the same way. Okay, So inside the code here, you can also allocate for local variables, which is non-existent, which means you're not actually adjusting the stack pointer, whether you're allocating or deallocating. It's just the template of the code being there, making it easier to handle stuff later on. But let's just say that we don't want to do it. Okay. So now the question is, what do we do with the first line of code? Because once you know how to do the first line of code, you can do the rest. The first thing is, how do you articulate the left-hand side of the assignment? Okay. In other words, how do you say it? Okay. The syntax is saying PTR points to A. Okay. The dash and the greater than symbol, I just say points to. Okay. But that is actually not very accurate. Okay. It's not a very accurate way of describing what is the left-hand side. So I will write this down. Okay. The left-hand side is member A of a structure that is pointed to by PTR. That would be the way that I say it. Okay, at least in English. Obviously, if English is not your mother tongue, you can convert this to whatever native tongue that you prefer. However, the structure, not so much the programming structure, but the structure of the sentence has to express that A is a member. And let me just kind of put quotes around the first A because otherwise it is a little bit more confusing. So member at the left-hand side is member A of a structure that is pointed to by PTR, which is not the same as member A of a structure PTR itself, because PTR is a pointer. It is not a structure. It is a pointer to a structure. Are we clear on that concept? Okay. So what I'll do is I'm going to put a halt instruction here, and then I'll go back to main, and you can see that when I write code, I jump around quite a bit because this is how I can debug the program, step by step. So over here, the first challenge is I need to find the address of var1, and then some of you are going like, oh, that's exactly where the stack pointer is pointing to. So we just have to push the stack pointer itself on the stack. Well, the answer is yes. Okay. However, it's not as easy as you think to push the stack pointer itself on the stack. Okay, so I will illustrate. So this is to reserve a byte, and then we just store the stack pointer on the stack. This would be wrong. Why is it wrong? Because what we really want to push is not the stack pointer. What we really want to push is the base of the frame. So if you execute a sequence like this, we adjusted the stack pointer to 1 byte below where the base of the frame is. So by the time we push it, the D that we are actually storing to that location is not the D that you want. It is 1 byte below what you want. Okay, so that's why this method does not work. So if you want to do it this way to do a really shortcut, because there's only one variable and it's always pointed to by the stack pointer most of the time, you can always do a CPR first. Okay, you can do something like this. So this way you are taking a snapshot of the stack pointer before you push it on the stack. Okay, so on line 43, at that time, register D, the stack pointer, is still pointing to the base of the whole frame, and you capture that. Okay, you copy that to register C, and then later on line 45, that's the value that you push on the stack. So this would work. Okay, so now the question is, are we really sure this is going to work? Well, let's go ahead and finish the code, and then we'll run it as it is, and then we'll find out whether the code works or not. So now we have to load the return address, or we have to push the return address on the stack, decrement D, stda, and then we continue execution at the function, which is called f, and then when it returns, we have to deallocate the parameter or argument. So how many bytes should I deallocate? Should I deallocate 1 byte or 3 bytes? Because what did we push on the stack? Did we push a structure on the stack, or did we push the address of a structure on the stack? The address. Yep, that's right. So there's only one increment. This also relates to C++ programming. So when you specify a structure as a parameter and not the address or pass by reference, it would actually push the entire structure on the stack. If you have a gigantic structure or object in object-oriented programming and you're passing by value, it would actually push the entire thing. It would make a copy of the entire object on the stack. Do you think that is efficient? It's not efficient at all. Okay. But it does give you the protection, right? Because if the function decides, you know what, I'm going to change the parameter, guess what? It's just a copy of whatever it was originally copied from. So you're changing a copy of the original, which is cool, okay? But in most cases, if your function is not modifying anything about the parameter, you can always add the word const, okay? So that the compiler will check, make sure that you are not changing the parameter itself, even when it's passed by reference or passed by pointer. Yep. There's no checking with that sort of thing. Const is an entirely a compiler feature for safety purposes. And in assembly language programming, you have no safety net. There's nobody checking your code. There's no guardrail whatsoever. Yes. So whether you use const or not, it will still compile to exactly the same code. The only difference is if you accidentally make a change to a const parameter, the C compiler will complain about it because you promised that you're not going to change this, and then you change that later on, so it will generate a compile time error. But if it but if you cast it first to a non-const thing, it will still let you do it and generate exactly the same code. So that's why high-level programming is good because you can rely on the tool to basically enforce certain rules that you think is reasonable. So that if you accidentally make a change to something, the compiler will complain about it and go like, "Hey, you said that you're not going to change this, and now you're changing it." So does that answer the question? Okay, perfect. So that's a good question, okay, because it is relating what we're learning in this class to general C, C++ programming, which is actually one of the main purposes of this class. All right, so as I was getting to here, I think that's all I need to do for now because I have made the call. Did I deallocate? Let's see, JMP. Yep, I did deallocate. Perfect. All right. So we're going to run this code. The focus of running this code is we will get to this halt instruction here, and I would like to see what is on the stack at that point. So getting back to the picture of the stack, this is also something that I would encourage all of you to do, is when you work on your code, think about what is on the stack and kind of give it a picture, okay? This document you can copy, so if you want to know, if you just want to go like, okay, I like this portion of the thing, I just need to erase the other side, fine. Go to File, go to Make a Copy, and then make a copy, and then you can make changes all you want. Okay. So now we know that we just pushed the address on the stack, and that becomes, is it PTR? Okay, that's PTR of the function f. These three belong to main, and that should be fc. Okay, that should be what I'm pushing on the stack. And then at that point, okay, at the halt instruction, I also kind of want to make sure that I know where the stack point is supposed to be pointing to. It is supposed to pointing to be. It's supposed to be. Nope. One more thing, I forgot the return address. So this is the return address from F to main. And I'm not going to go find, I mean, I can, but I don't want to spend the time. So we'll just go ahead and say the stack pointer should be pointing here, and that's what the stack should look like at this point. These are unknown, they are uninitialized. This one, I know it is supposed to be a 08, okay, so we'll just kind of put a 08 here. This one, I don't care at this point. So we'll go ahead and test the code, okay, make sure I save it first, like so, and then we just run it again. So this is kind of how I would imagine that you would use this method in order to do your homework, is to do it step by step, okay? really confirm what is happening on the stack, look at the trace, because guess what? That is how you study for the final exam. This makes sure that you understand all the concepts, and by doing it, okay, by looking at the trace and go like, oh no, this is not the way it's supposed to be. I forgot about this. That is how we study, or how I would imagine people study for this class. All right, so we're going to take a look here. Okay, so we have 08, the return address from main to the entry code push on the stack. And then the next thing that we push on the stack is FC, which is the address of var1 of main being pushed on the stack as parameter PTR of F. And then we push the return address, and then we get to the halt instruction at the entry point of F. So that is reconstructing what we thought would be the case in the code. So this trace here, by looking at all the fragments that we push on the stack, is actually if we reconstruct everything into a kind of contiguous region of memory, that's what it would be looking like. Are we good so far? Yes. All right. So is the process of writing this kind of code understood as well? It's not really just the code, but also the process of writing the code. Is that okay? Are we understanding all that stuff too? The process? Okay. Okay, so you're doing this. Do you want me to further explain any parts? Yes. Yep. There is a certain structure to it. So the important part of writing code in assembly is clarity. You need to have absolute clarity of the C code to begin with. So when you look at the C code, you kind of know, okay, this is underneath the high level language. This is what is happening. Maybe not even expressed in stack operations or TTP ASM, but you kind of have to understand, okay, this needs to be pushed on the stack, and then we retrieve that. This is a pointer to something. It is not a var, it's not a structure itself. So you have to be very conscious of what each line of C code is actually representing. And then implement it in assembly to make sure that your assembly code ends up with exactly the same effect as the C code. Well, that's why I gave you assignments. That's why I gave you the assignments that I gave you, or will be giving you as well, is to get you guys to have more kind of hands-on experience, because the whole debugging process, if you write every single program and it works perfectly the first time, you are not going to be learning as much as, oh, okay, I make a poo-poo here, the program didn't work, because you have to go back and diagnose why is it not working. And by the process of diagnosing, you are actually learning, you're deepening your knowledge about what you're trying to learn here. Yep. Okay. Yeah, you can even kind of put your own thoughts, perhaps into either Notebook LM or into a gem in Gemini. So you basically point Gemini gem to a Google Doc. That is your notes. That is your understanding. You're writing about the understanding. Then you can use that, use AI to help you understand, okay, what am I supposed to do here? So I haven't really tried it with Gemini Jam, but ChatGPT, custom GPT works fairly well with that sort of thing. All right. So now we can kind of, okay, wait. Are there any further questions before we proceed? No further questions. All right. Well, then we're gonna move on, check out this halt instruction, and now we have to figure out So once again, I'll do the super annoying thing of not commenting the code as I talk about it, okay? Because you can I'll give you the code at the end of the lecture. I'll give you the source code and the C code, okay? But I think it might be helpful for you to kind of replicate the experiment itself and then start to document the code, okay? So this is exactly what I'll do, okay? But I will verbally explain what is going on. The right hand side is not a problem. It's just a zero. I can deal with that later. Okay, so I'm going to deal with where the left hand side is, or what we call the L value of the left hand side, which is the address that needs to be changed. So we know this is a member. Okay, this is member A of the structure that is pointed to by PTR. So which part do you think I need to figure out first? Hmm. Well, you mean the member itself? No, we don't, because all we have is a pointer as a parameter. So, okay, read this sentence here. Okay, the left-hand side is, okay, that part is not important. We're dealing with member A of a structure that is pointed to by PTR. So that means when you see the word of, that means whatever is on the left-hand side of the of cannot be figured out until you know what is on the right-hand side of the of. Does that make sense? Okay. I'll say that one more time because I see a few blank faces. I'll say that one more time. If your objective is to figure out whatever is to the left-hand side of the word, the proposition of, you first have to figure out what is to the right-hand side of the same proposition. Does that make sense? Well, or someone can decide to change the ordering of A, B, and C at some point. So don't make that assumption, okay? You can basically say I can trust the label definition, but I should not be implying which one is the first one. It's not caller callee anymore because these labels are known to the entire program. So it's not about the caller callee. This has its own reading module. Okay, so there's another reading module on just structures and arrays. Yep. So you might want to. So that will capture what basically everything that I'm going to talk about here. Yep. Okay, so assuming that is the case, okay, so now we need to figure out what is the structure that is pointed to by PTR. Okay, so the next word that we want to focus on is this little word here, by. Okay, so if you need to figure out whatever is to the left-hand side of the by, don't you think we have to figure out what is on the right-hand side of the by first? So that means, oh, okay, forget everything else. I need to figure out what is PTR first. Okay, so that's dependency based reasoning. Yes, I just gave it a name. Okay, but that's how I think. Okay, the way I think is I look at a bunch of stuff. Okay, there are a few concepts here. There's a member, there's a structure, and there's a pointer. Okay, there are three things here. So how do I figure out what is the last thing that I need to figure out, and what is the order that I need to do it so that I can get to eventually what I need to get to. Okay, so the analysis based on dependency basically says, well, the first thing you need to do is to get to pointer. Okay, so I don't want to worry about anything else. I just need to get to pointer first. What is pointer? Pointer is a parameter. So how do we get to a parameter? The same way that we get to a parameter in all of the previous discussion of this class. Okay, the only way we can get back to the pointer is this label here. But what is that label representing? That label is representing the number of bytes from the base of the frame to, in this case, parameter PTR. That's all I'm given with. But the caller callee agreement also guarantees that if the caller did its job correctly, that's exactly where you'll find PTR. Okay, So the code to do this, okay, the first part we have done this already when we talked about parameters alone. So that would be something like LDI, I can choose C this time. Okay, this is the offset from the base of the frame to PTR as a parameter. Well, we have to add the base of the frame to the offset so that we get to the address of the parameter. Unless in some other kind of awkward situation, the stack pointer most of the time points to the base of the entire frame. So by adding the stack pointer to the offset, it will be the same as adding the base of the frame to the offset. So now you'll see becomes the address of PTR. So, okay. So the fact that PTR itself is also an address of something does not change the discussion, okay? Because I still need the LDCC in order to get to the value of PTR. The value of PTR does not equal to the value that PTR is pointing to. This is really just the parameter itself, okay? The parameter itself is an address to somewhere else. I don't even care what it is, okay? I just need to get to the parameter first. So once I have this, C is now PTR itself, then I have to be careful because PTR itself is the address of a structure. And we want to access a particular member of that structure. So that means, okay, we'll keep register C the way it is. We're going to put it into a different register here, which is the offset of the member that we need to access. Okay, so this is a LDI. So register B is now containing the offset from the beginning of a structure to member A of that structure. And it turns out to be 0. But as I said, if somebody decides to, okay, I want to add Z as a member before A, then it won't be 0 anymore. So I would not make assumptions about, oh, this is just 0. We don't have to do this. Okay. So this is the magical step, okay? The magical step is to add B and C. So when you add BC or CB, it doesn't really matter one way or the other. Now B, in this case, it becomes the address of member A of the structure that is now pointed to by PTR. Okay, I just made a whole bunch of claims, okay? But I'm going to finish this code by, so at this point, register C is not really useful anymore, so I can kind of clobber that, okay? ST B C. So that should accomplish what we set out to do, on, of the C code that is now commented out on line 24. I'm not going to move on until I verify this is working the way it's supposed to. Is that making any sense? Because otherwise I'll just be replicating the same mistake multiple times. Why would I want to do that? Are we good so far? Okay. Yes. Yes. The labels related to the structure definition are quote unquote global to the entire code. Yep. All right. So I'm going to put a hold instruction here so I can stop the program right at this point. Okay. So make sure I save the code and then run it. And you can see that I don't write a whole lot of code, like maybe up to 10 lines or so before I put a hold instruction somewhere and just kind of go like, okay, let me make sure I'm not making any mistakes. So now we go back here. Okay, we go back to the assembler and we are expecting, okay, so now the map becomes useful because we just said we're going to put a 0 here. So I am looking at a store to location FC with a value of 0, 0. That's what I'm expecting. So now we go back to the trace and we are looking for, aha, we see that, okay? Now, this is super duper helpful because if you put in the comments, okay, based on verbally what I described, the comments would actually show up here as well. So that means you can actually read the comment of the instructions that get executed and also look at the side effect of the execution of those instructions on the same in the same spreadsheet. But then you can also see how the registers got updated. You can also see how the memory locations got updated, alongside the instructions that hopefully will be commented. Are we good so far? So this is the kind of tool that I give you to understand the material that we are talking about in this class. Okay. And I would certainly hope that you try your best to make use of that tool because otherwise it really is, as you said, really difficult to visualize or to understand because it is extremely low level. You have to make because you have to maintain several things at the same time. You have to maintain the source code. Okay, you have to look at the source code here, which hopefully will be commented, and then you have to look at the actual structure of the memory locations. What location on the stack is supposed to be used by what, and then you look at the trace, which leaves behind, little fragments like this, okay, in order to show you that, oh, okay, this is when we update member A of the structure that is pointed to by PTR. But nothing says here that this is the member A of the structure that is pointed to by PTR, unless you put in comments in the code. So that's why I encourage you to put in the comments and then you rerun um, River Spider so that when you look at the trace, you can see it. Now, the other way you can also do it, if you take a snapshot at the end of the lecture when we are all done with the code, you can also just go here, make a copy, and then you go to the source tab and then add your comments to the source tab because it would accomplish exactly the same thing. Okay, I can illustrate. Okay, so let's just say that I want to comment this line here, but I still don't want to do your own homework assignment. So we'll just say that text says blah blah blah. Okay, that is probably typical of me. Then when you go back to the analysis tab, yep, it's here. Is that okay? Are you guys starting to understand how to use this tool? Okay, very good. All right, so we're going back to the code because I want to finish this. All right, so I am going to take a shortcut here. Okay, so I'm looking at this and go like, it looks like I'm gonna have to repeat all this stuff again and again. Hmm, I may not want to do that. Let me just kind of change that register to A. So I'm preserving register C at this point. Is that okay? So now you have to write the code. You have to write the comments to basically track what each register contains. Okay, that skill is going to be super useful for the final exam because in the final exam, I will give you code like this, and then you're supposed to know what is wrong with that code because I will inject problems into the code, and you have to identify where the problems are and how to fix those problems. I will give you the C code. Okay, I'll give you the faulty assembly code. You have to find out where the faults are and how to fix them. Okay. Okay, so now we're using all three spare registers. Register A is really just storing the value that we need to store. Register B is kind of like floating around. Okay, we can override it. Register C has PTR in it. Okay, so now we look at this one here and go like, okay, we are just gonna keep PTR, but we can change register B. Okay, so we now load register B to, okay, I think this is probably the better way to do it. Not the only way, but we're going to do it this way. So now we add again BC. So now register B after line 34 becomes the address of member B of the structure that is pointed to by PTR. So I just saved myself a bunch of code because I don't have to recompute C. And with register A, I can just do this, okay, so that it goes from 0 to 1. Yeah, but I'm going to do the more obvious one like this, okay? And then we just say store that to whatever B is pointing to. So I just did some optimization. And in the arena of programming, optimization is introduces a lot of bugs, okay? Because you're basically keeping track a lot of tricky stuff to optimize, things, and your mind actually has to keep track of the context. So that means, okay, I am not really sure whether this is going to work or not. Test run it again, okay? So test running it often does not mean that you're doing it by trial and error. All you're doing is you're confirming that one step is working before moving on to the next step. Okay, so this is not the same as trial and error. Trial and error means you just kind of try random stuff without reasoning out what it is going to do. Well, I know what it's supposed to do. I just want to confirm that. All right, FD is getting a value of 0, 1. According to the map here, that really is where member B is supposed to be, and getting a 0, 1 is exactly what I want. Okay, cool. So that means the approach works. So if the approach works, okay, we will go ahead and do one more optimization. Then I go like, okay, that is kind of cool. What about this? Now, this is totally bad programming, okay? I'll explain why it is totally bad programming, but it's going to work in this case. So should I explain first, or should I show you that it works first? Explain first? Okay. So register B already has the address of member B of the structure that PTR is pointing to. Register C, according to what I remember about the structure, is right after member B. So that means by incrementing B, register B now points to member C of the structure that is pointed to by PTR. Okay, what about register A? Well, I just put a 1 into it last time. Incrementing 1 means it's going to be a 2. Okay, so it should work. But why is it bad? Because this kind of code is super, I would call brittle, okay? Because if somebody decides to reorder the members of the structure, this is going to break, okay? Because I also have to go look for this code too, because if I forget that I have done some optimizations like this, and it's 2 weeks later that somebody decides, you know what, we also want some these other members, kind of between member B and member C, my code is not going to work, and it will take me a long time to find out why it is not working. We are we are optimizing based on, as you're correct, based on assumptions. Um, we you can do that using a tool. The tool will have to rescan how we are making changes to the original definition of the structure and then decide that, oh, okay, we can optimize it like this. But without a tool to do that consistently, this is really brittle. But I will show you that it does work. Okay, so we'll save the code, put a halt instruction here. Okay, save the code and then run it, and then make sure that, oh, okay, just ran the wrong code. I'll let it finish because otherwise it might get into an intermittent, get into a state that I wouldn't want to get into. There we go. Okay, so this would be the right code. So this time I'm expecting a 2 to be written to location FE in the trace. So now we go back here. Okay, go back to the assembler, scroll down a little bit and go like, yep, it worked. Okay, but as I said, this is very, very brittle code. Okay, if I change the definition of the structure, most likely it's going to break this. So that means, yeah, it does work, but I will keep the code as it is now just so that you can document it. Okay, so I would say documenting lines 38, 39 is super important because that relies on you being able to track what was in register B and also in register A from before. All right, so this code is kind of important because even on this line here, on line 34, it still relies on you knowing what is in register C, which was last changed on line 27. And then on lines 38 and 39, it gets even worse because it relies on you knowing what is in register B and also what is in register A from lines 34 and line 35, so that you, in the context of the C code, PTR points to C gets 2. Now you have to go like, okay, this is really a kludgy kind of code. It works, it is efficient, but it is not a good way to do it. Okay, so I will now save this code. Oh, wait. Let me take out this halt instruction, make sure the code works overall speaking, and then I'll post it on the website so that you guys have access to it. Whew. Okay. Yep. Yeah. So if you want to future-proof the code, then what you want to do is to change lines. Lines 34 and line 35 is not a problem. Okay, they are already future-proof. The one that is not future-proof would be line 38 and 39. So instead of doing it this way, you probably still want to do a LDIA with 2, and then also um, reload x underscore c into register B and then add c to B again instead of just incrementing B. Okay, so double check, okay, make sure that this code still works. Okay, everything up to here, we just put a halt instruction. We remove the halt instruction. So now this code returns to main. Main is going to deallocate. How do we know it's deallocating? We look at the stack pointer. The stack pointer went from FC to FF. That's a deallocation of 3 bytes. And then we return back to the main code. And now the stack pointer is balanced. We are now at the correct halt instruction. So now the program is all working, which means I can now package the whole thing and then put it into the announcement so that you have access to exactly the program that we were talking about. So in the future, if you guys have any idea of, okay, I want to see how this is implemented, you can always send a request to me. Okay, I don't have a problem taking requests even in class. Okay, so if you're in the class and you go like, okay, this reminds me that I really want to know how this thing is implemented. Okay, depending on whether it's relevant to this class. If it is, and I see that we can do it within a reasonable amount of time, I can do it in class too. Yes. Yeah. Yep. Yep. But that has nothing to do with structures. Yeah. It does have to do with recursion, but has nothing to do with structures. So yes, I can do that. Oh, you mean the actual moving of the disk? It cannot really move the disk per se, but it can leave behind a log of what disk is moved from which pole to which pole. Okay, we can do that. Yep, we can do that at some point. Remind me. All right, so the lecture portion is done, and we'll move on to the lab. So the lab today is recursive calls. Okay, and there's the assignment that goes with it. And then recursive calls has a passcode and an access code of holodeck. The reason why I chose the word holodeck is because recursion is kind of like you're in a holodeck, and then you're getting into a holodeck within the holodeck, which turns out to be one of the plot lines of Star Trek: The Next Generation. Okay, if you don't know what I'm talking about, it's okay. Holodeck. All right. Yep. You should be able to get into the lab right now. And then I will package up the code here. So we'll do a zip struct.zip struct.c struct.ttpasm and then put it into one of the announcements. All right, there we go.